Hello students, in this video we will be discussing the small signal model of JFET. First of all we discuss the input impedance Zi. Zi of JFET is infinite ohm. It is approximately equal to 10 raised to 9 ohm. This is because of the fact that the input side or the gate side is always reverse biased to a very high voltage. Hence we assume it as there is no current is taken by the gate terminal and hence the input impedance is taken as infinite value. It is approximately 10 raised to 9 ohm for JFET and in the case of MOSFET it is 10 raised to 12 to 10 raised to 15 ohm. So this is because the reverse bias junction takes no current. Next is the output impedance ZO. It is typically represented as YOS. O signifies the output and S the source terminal, which is the component of an admittance equivalent circuit. So ZO is defined as the drain resistance, which we have discussed in the previous video, RD. And this is equal to 1 by YOS. This value is the admittance. So RD is equal to delta VDS by delta ID at a constant VGS. So this value range from the value of output impedance RD or ZO range from 20 kilo ohm to 100 kilo ohm. Now this is the small signal low frequency FET model. Here this is the gate source junction. We represent this as current source. This is a Norton's current equivalent circuit. So this is GM into VGS and here we represent the output impedance or the drain resistance RD and we have the drain source voltage VDS. This is the equivalent circuit of that. Equivalent circuit of small signal FET connection. This is given in equation in the figure 10.8a in Millman. So GM into VGS is current source connected from D to drain to source with current flowing from D to S. So this portion is taken as open. Why? Because the input side we know that it has an infinite resistance and hence represented like this. So Zn is represented by an open circuit at the input terminals and the output Z out by the resistance RD. This is the equivalent circuit. In this model, current generated depends on the input voltage. Current generated ID depends on the input voltage. In situations where RD can be ignored, the equivalent circuit is simply a current source whose magnitude is controlled by the signal VGS and the parameter GM. We get the current as the current source as GM into VGS. So if we take RD, if it can be ignored, that is simply a current source. So the small signal FET circuit is equivalent to a current source, right? It is already a voltage controlled device, which we know earlier, and also no feedback exists in a low frequency model, and voltage amplification is not altered. So by this model, no feedback and hence the voltage amplification is not changed. Now this is the high frequency model. In the high frequency model, there is some difference here. Some node capacitors are taken into account. So here we have a capacitor, here also we have a capacitor, and the outside we have a capacitor. This is our current source. So CGS, this is the barrier capacitor between gate and source. Right? Now CGD, it is the barrier capacitance between gate and drain. And here is the CDS, which is the barrier capacitance between drain and source. So because of these capacitances, feedback exists between input and output circuits. So here this is coming into the input side, and the voltage amplification is dropped in the case of high frequency model. Since the frequency is increasing in the model, so the voltage amplification is affected in the high frequency model. These are the range of parameter values for a FET. So GM has value 0.1 to 10 milliampere per volt, RD 0.1 to 1 million, CDS values, RGS, RDS, etc. and the similar values for MOSFET also. Okay.